moving further forward with our consideration of projectile motion, the next one is going to be a horizontal projection. So we first of all dealt with, in the last video with dropping, and then looked very briefly at a vertical projection. We're now going to consider horizontal projection. Point to note here is that the acceleration due to gravity only acts vertically, and so that means we can sort of split things up. So the acceleration due to gravity isn't actually going to affect any horizontal motion. So we can then consider the fact that for vertical acceleration, we would say that the vertical acceleration is going to be the acceleration due to gravity, and that's going to be negative 9.8. So we'll deal with down as being negative down as being the negative direction here. So that's negative 9.81 meters per second squared. But horizontally, because we don't have any air resistance, there are no other forces acting on the object, the horizontal acceleration is going to be 0. Notice that I've used subscripts here, so I've used a V here and a H there to indicate the horizontal and vertical components. So we'll do that to clarify whether we're talking about horizontal motion or vertical motion in these scenarios. So considering that we've got these two accelerations, it's really important to note that the horizontal and vertical motions are effectively, they don't really affect each other. And the way that we describe that is that horizontal and vertical motion, or motions, are independent of each other. So that means that we don't have anything happening in the vertical direction that will ultimately impact on what's happening in the horizontal direction. So what that means is that we actually need to do two sets of calculations. And those two, basically, if we sort of spell that correctly, if we look at the equations of motion now in horizontal and vertical directions. So what we would have vertically, we would still have all of our equations as per usual. So the vertical velocity would be equal to the final vertical velocity is equal to the final initial vertical velocity. Notice how easy it is to stumble over the words here. So we'd have that equation for vertically. We'd then have this one as well. So half at squared, and in the vertical direction we'd also then have vv squared is equal to uv squared plus 2avsv. So all the subscripts start to get a little bit annoying and fiddly to work with, and the last one, s in the vertical direction, would be uv plus vv on 2 multiplied by t. So we've got those four equations that we can use in the vertical direction. Now if you look at the horizontal direction, it's a fair bit easier. You'll notice that in most of these equations we have acceleration included. So in the first one, if we have 0 acceleration, we end up with vh equals uh. Not particularly useful. There's nothing that changes there, so we can ignore that one when we deal with the horizontal component. If we look at the next equation, this last term in the horizontal, so the horizontal acceleration would be 0, so that term would disappear, but we'd be left with sh is equal to uh multiplied by t. Again, down the bottom here, this term, if we were looking at the horizontal equivalent, this last term would be equal to 0, so that term would disappear, so we're left with vv squared equals uv squared. Again, nothing particularly useful there. And down the bottom, uv plus vv over 2, because there's no acceleration, u is going to be equal to v, as we saw from this equation, and so we'd end up with sh is equal to uh times t, so we end up with this equation again over here. So horizontally, we only have one equation that we need to deal with. sh is equal to uh multiplied by t. Now you'll notice that the only quantity here, the only quantity that links the two motions is time. So basically what you need to consider here is that if you're wanting to figure out something that's happening horizontally, you first need to know over what time that occurs, and you need to use your vertical components to figure that out. So for example, if we were looking at say the height of a cliff, and an object gets thrown off that cliff at a horizontal speed, let's say it's 20 meters per second, the time that it takes for the object to then fall to the ground, we would use the vertical component. So notice that initially the vertical component here, uv, is equal to 0 because it's all horizontal projection, and that then means that we'd use the vertical components to figure out how long, the time that it took to fall that way. We could then use the time to figure out how far out from the base of the cliff the object was to land, considering the horizontal displacement. So using the time is the critical thing that will link the two quantities together. Again, we'll do some problems in class looking at those ideas and some of the ins and outs of those scenarios. The last thing then, the last scenario, that basically just takes the horizontal projection one step further, is projection at an angle. And for projection at an angle, it's basically just, like I said, just a step up from horizontal projection. As we've said above, the horizontal and vertical components are independent. So if we had this object then that instead of being projected horizontally was projected at some angle, so here's the horizontal and we projected at some angle theta, if that's our initial velocity u, what we need to do is to resolve that into components that are both vertical and horizontal. So for projection at an angle, the initial velocity must first be resolved into components. And I'll just really quickly go over that resolving. Again, because it's now vector, vector calculations, you may want to refer back to topic 1.3 for a bit more detail. So what we have in this situation then, if we want to resolve this into components, we're going to need to break it up into a horizontal component this way, we'll call that UH, and a vertical component that way, that's UV, and we know that that's a 90-degree angle in there. So what we can say here using trigonometry is that the horizontal component is going to be equal to the vector u cos theta, and the vertical component uv will be equal to u sine theta. Now you need to be careful here about the directions again. If you're using up as positive, if the object was then being projected down, then or down at an angle, you then need to make sure that the vertical component had a negative at the end. When you write the value for the vertical component, you need to make sure you indicated that it was negative. Usually speaking here, I'll just make one more note here, this is only applicable when theta is measured from the horizontal. If it was measured from the vertical, you could either change them around, or you can figure out the angle from the horizontal and use that instead. By that I mean, if say you had something was projected at this angle here, then you could use that as the horizontal, that as the vertical, or you could redraw this triangle in as we saw before, figure out what this angle is, and then use that instead. Either way, you could do either of those two will work, and again we'll look at some example problems in class. The last thing then to say about this scenario is the final velocity needs to be we'll need to figure it out using a combination of the two. By that I mean we need to determine the resultant of the two final velocities. So the resultant of VV and VH. So if an object strikes the ground and it has let me do it this way. It has a horizontal component that's in that direction, and it has a vertical component in that direction. So you can go through and use the equations of motion to figure those two out. The final velocity then is that vector there. We'll call that angle theta, and that's going to be our final velocity v. So again, as we've seen with vector calculations, the magnitude of the final velocity we can figure out using Pythagoras. So that's going to be the magnitude of the horizontal component squared plus the magnitude of the vertical component squared. Notice I'm just using the vector notation to identify that we are actually dealing with vectors here. And the angle theta would then be calculated using trigonometry, and in this case it'll be the inverse tan of the magnitude of the vertical component over the magnitude of the horizontal component. Again, be careful with the direction here. If it's below the horizontal, then you should state that when you calculate the answer. So let's say it was 20 meters, V might be say 45 meters per second at an angle of 23 degrees below the horizontal. If you just said at an angle of 23 degrees, that could be 23 that way. So you need to specify very clearly that it's 23 degrees below the horizontal in the answer. Once again, we'll have a look at some example problems in class and try and bed this whole aspect of projectile motion down much more effectively.